Hello grade 11 students. Right now we are going to continue the structure of the atoms, chapter 2. Now we are learning from chapter 2.7, the arrangement of electrons, energy levels and orbitals. On the previous page, we concluded that the atom is made up of very dense, very small nucleus containing protons and neutrons. Now turn our attention to these electrons. We shall see that they are not distributed randomly in this region of space. They occupy specific volume regions called orbitals, which have high specific energy associated with them, energy levels and emission spectrum. When gaseous atoms are given energy either by heating them up to several hundred degrees or passing the current through them, electrons become excited and move from lower energy levels to the higher energy levels. When these electrons are excited, we call these electrons undergo hybridization. Okay, can also move from higher energy to lower to higher energy levels by absorbing specific frequencies of light. This leaves dark absorption lines in the spectrum of light transmitted through the gas. It was these absorption lines that provided the first evidence for a new element discovered in the outer regions of the Sun. It was named helium, after the Greek word for the sun, helios. The technique of atomic absorption spectroscopy is widely used today to measure accurately the concentration of calcium and sodium in blood sample or elements contained in a sample of steel alloy. Eventually, the excited electrons lose energy again by falling down to lower energy levels. During this process, they radiate visible or ultraviolet light in specific amounts of packets called as photons. Okay, this is the figure 2.11. The emission spectrum shows only a very few specific frequencies are emitted, and these are unique to an individual element. So each element they have their own frequency that makes the frequency transfer in the spectrum of light makes people can see what color the element is. Okay, so this one, like sodium vapor, the color is yellow. The frequency is 10 to the power of 14. These are the wavelength of yellow color, and then this one is the white light. So they have their own spectrum. Cadmium is the color is turquoise green. What are the frequency? There is a certain frequency. Okay, do we need to learn this frequency? We need to know. Okay, so there is a relation between speed of light, frequency and wavelength. V equals to F times lambda. That's we need to know, and then in the calculation there will be some list of the frequency and then also the wavelength for specific colors. So it's not need for us to remember what color in what frequency in what wavelength, because there is data booklet. We just need to know. Energy of a photon of light is related to the frequency Planck's equation. Okay, we are not fall into the too much calculation of this Planck equation. We need to know that if photons of a particular frequency are being emitted by an atom, this means that the atom is losing particular amount of energy. The energy represents the difference between two states of the atom, one more energetic than the other. This is in a specific atom, in one type of atom. The spectrum of the simplest atom, hydrogen, shows a series of lines at different frequencies. This suggests that the hydrogen atom can lose different amount of energy, which in turn suggests that it can exist in a range of energy states. Transitions between various energy states cause the photons to be emitted at various frequencies. These energy states can be identified with situations where the single hydrogen electron is in certain orbitals at specific distances from the nucleus. As we can see here, part of hydrogen spectrum showing the corresponding energy transitions. This one, this one, as we can see, the frequency of the electrons, that the energy that it can move. This one is the ionization. So this one, excited electron falls to n equals to 2, which is the uh, shell. Okay, this is the energy, the level of the energy 2, 3, 4, 5, 6. It's not necessary for us to know what is the exact amount of energy. We need to know that there is E1, E2, E3, E4, E5 and E6, and this one is the electron can move. When the electron is moving, it can gain energy or lose energy. The energy is in certain frequency and also in a certain wavelength that makes us able to see those light, those colors. And then quantum theory. The fact that only certain frequencies of light are emitted rather than continuous spectrum is compelling evidence that the energy of the hydrogen atom can take only certain values, not continuous range of values. The basic notion of the quantum theory. We said that the energy of the hydrogen is quantized. Rather than continuous, it can lose or gain energy by losing or gaining a quantum of energy. Good analogy is staircase. When you climb a staircase, you increase your height by certain fixed value. You can be 4 steps from bottom, 5 steps, but not 4 or a half steps up. By contrast, if you were walking up ramp, you could choose to be at the height you like from the bottom. It turns out that the energy of all objects is distributed in staircases rather than in ramps. And then the staircases represent the shell. So we shall see the quantum, this one, energy level in the atom. So hydrogen is very small spherical atom, only 2 particles, a proton and an electron. Apart from energy of movement, the only energy it can have is that associated with the electrostatic attraction between its 2 particles. The different energy levels are therefore due to different electrostatic potential energy states where the electron is at different distances from the proton. So this one is the energy level associated with different distances of the electron from the nucleus, are called as orbitals. Okay, so there is the principal shell number. 1 is 1, 2 is 2, 3 is 9. So the number of orbitals in the nth shell is called as, the formula is n squared. The orbitals are arranged in shells. Each shell contains orbitals of roughly the same energy. The shell with the lowest energy contains only one orbital. Shells with higher energies further from the nucleus contain increasingly large number of orbitals according to the formula. Okay, so this is the first shell, the second shell, the third shell, the fourth shell, the fifth shell, and then the sixth shell. Number of orbitals. Okay, subshells and the shapes of orbitals. Electron probability and distances from the nucleus. Let's see. This one, as you can read in the textbook, in the copy of the textbook, there is an electron, and then this one, the first shell is called as s orbital. The second shell contains s and p orbital. S orbital is spherical symmetrical. So the shape is spherical. And then the second shell of the 4 orbitals in the second shell, one is spherical symmetrical like orbital in the first shell. This is called as 2s orbital. Its probability curve is shown in figure 2.16. The other 3 second shell orbitals, which is in 2p orbital, it is called 2px, 2py and 2pz. They do not overlap with one another. These electrons, the shape is like a dumbbell. Okay, so like a dumbbell here. Now, this one is the shape of p orbitals. This is the arrangement of pz. This one is py. This is px. Okay, the y. This one, the arrangement, how the shape of the orbitals are look like. And then the third shell, spt. spt also the same as is spherical symmetrical, and then p is consisting of px, py and pz, while d is consisting of dxy, dxz, and then dyz, dx square y square, and then dz square. So this one are the shape how it looks like. Okay, this is the, we need to know that there is d orbital. D orbital consisting of five orbitals. Okay, the fourth shell, which is called as SPTF. There is an F. Okay, F, how does it look like? The shape of F orbital is like this. This is already very complicated. Not all of us can draw 3 dimension to make into this shape. So in A level, they maximum only ask us to draw the shape of d orbitals. Okay, so shells and orbitals summary. The number and type of orbital within different shells are summarized in table 2.4. The shell number, the orbital within the shell. Number of orbital each type, the number of orbital in each subshell. So S is 1. And then in subshell number 2, S is 1, the number of orbitals, and then P is 3. And then in the third, D is containing 5 orbitals, and then F containing 7 orbitals. What is the meaning of orbitals? I'm going to explain. Then putting electrons into orbitals. This one, the atom's different element, we have to see the atomic configuration of the atomic configuration of SPTF. How to draw? Okay, how to draw for this 2.9? I'm going to explain using this diagram. Aufbau principle. This one is the how the atomic configuration look like SPTF. So as 1, this is 1, 2, 3, 4, 5, 6, 7. These are called as the quantum number. S meaning the subshell. And then this one 2, it means the maximum number of electron in one subshell. This one S, we know that S contains 1 orbital. In 1 orbital there are 2 electrons, so S can maximum occupy by 2 electrons. And then P maximum has 6 electrons. We can put less, but we cannot put more than 6. It has the maximum is 6. So there are 3 orbitals. There are 3 orbitals in P, Px, Py, and Pz. And then the third shell, there is a addition D. The subshell D contains 5 orbitals. As I described before using the diagram from the textbook, it is called as D orbital, a D subshell. And then 4th, 5th, 6th, 7th, they contain F, an addition, F subshell. The F subshell maximum can contain 14 electrons. One subshell, the F subshell, contains 14 electrons, and then if 14 divide by 2, why divide by 2? Because one orbital can only occupy 2 electrons. So in the F subshell there are 7 orbitals. How do we write the electronic configuration? Is by using this diagram arrow. So this is start from 1s2 and then 2s2 and then 2p6 3s2, then 3p6 4s2, then 3d10 4p6 5s2, and then 4d10 5p6 6s2, 4f14 5d10 6p6 7s2. So this one continues, so the line has to be diagonal. Why diagonal? This is because the writing based on the energy level. 1s2 is having the lowest level, but it has the strongest attraction with the nucleus. 2s2 has higher energy level compared to 1s2. So this one also the same. So 2p6 and 3s2, they are almost at the same energy level. There is increase. So we are not supposed to write 1s2, 2s2, 2p6, 3s2, and then 3p6, 3d10. From 3p6, it must continue to 4s2 first, not allowed to be 3d10 because of the energy level. 3d10 has more energy level than 4s2, so we have to state the 4s2 first. So that is the reason why the lines diagonal. Next, how do we put electrons? We write like this. Okay, how do we put electrons? Is like this. Like this first. Okay, lithium consisting of 3 electrons. So this is 1s2. This is 2s2. So 1s2, 2s1. Because total 3 electrons. So 2 plus 1, 3. We count the electron from the uppercase number, not from the quantum number. Okay, so beryllium is 4. First, we have to write the electrons, which is the same. This one, up the arrow and then down. Not allowed to make up. Everything up. In one orbital, there must be one up, one down. What is the reason? In the next session, I will explain. And then this one, nitrogen, consists of 7 electrons. So 1s2, 2s2, and then 2p3. This one has to be all orbitals must occupied first. And then after all orbital occupied, and then we use the down arrow to fill the next one. Look at sodium. Sodium 11. 1s2, 2s2, 2p6 and then 3s1. So after 1s2 1 2 2s2 1 2 and then 2p6 1 2 3 4 5 6 and then 1 go up. The last one cannot, for sodium cannot be arrow go down. The arrow must go up, the first one. And then this one is the how it is arranged. Like iodine is 1s2 2s2 2p6 3s2 3p6 4s2 3d10 4p6 5s2 4d10 and then 5p6. Later I'm going to tell you in this next session what is the meaning by the last quantum number and also the last or the last subshell. There is a meaning. Okay, so and for today we are learning about how to put the electrons, and then when the electrons jump from higher level to lower level or from lower level to the higher level, there is an energy, either gain or lose. Those energy has frequency and wavelength. The wavelength and frequency is in spectrum of light that makes us able to see the color.